Glad to see you all here. This is kind of a new event for us. We had a great start to our thesis readings yesterday. Joy Green did a great job sharing her thesis with us, and we have one more thesis reading this afternoon, which will be Ian Balcarras at 3:30. Don't miss that one. And sometimes what we've done when we've only had a couple thesis readings is we've sort of filled up some of the space in our week, which otherwise sometimes has more thesis readings, with things like we've done faculty forums a couple times when that's happened, and I think this is maybe the first time that we've done alumni research presentations, and it seemed like the perfect time to take advantage of the fact that we could have some alumni visiting and were engaged in all kinds of exciting projects and share some of that with us. So we're really delighted to do this new experiment. And I want to, we've prayed for the alumni a lot when they were here. So instead of praying for each one like we do for the thesis, I'm just going to pray once for all of them this morning. I think maybe you can handle it. So let's begin with a prayer to bless the morning, and then I'll introduce our first alumni speaker. So God, we begin this morning just full of gratitude. Easy to be full of gratitude on such a gorgeous day, and we thank you for that. Thank you for the life of all the friends, new and old. Thank you for the joy of people returning. Thank you for the joy of people excited for completing their work. And we just pray for your presence to be in and through it all. So fill this room this morning, God, with your presence. Help us to see the way in which you're at work in such diverse ways in the world, and really bless the speakers as they share with us this morning. Amen. So our first speaker. Now, really, primarily, I know Matt Balcarras as a ping pong player. In fact, so he plays a very mean game of ping pong, and in fact, I just was reminded last night when I met him again that he actually never took any of my normal classes. One Europe class, I think, is what we figured out happened. So he's been good at avoiding me in the classroom, but not avoiding me elsewhere. So which is great. So I really have appreciated Matt's friendship over the years. After he came here and completed his degree with us, he went on and got a master's from the University of Edinburgh in philosophy. And then in one of the most unique flip-flops that we've seen among SSU alumni, he went on to York to do a PhD in neuroscience. So that does not happen every day. But we are very delighted that it did, and it really shows the kind of interdisciplinary mind and more interdisciplinary in the science direction than we very often see. So it's great to have a taste of that today. So Dr. Matt Balcarras, welcome here. Yeah.
It is very exciting and an honor to be here. I was hoping that this, oh, look at this one, stay awake. Nobody look. I was hoping that this opening shot was going to be a shot of me, but I don't have any pictures of me from my time here proper, so this is supposed to be a picture of me. Because the last time I stood in this room and talked was 10 years ago, in 2006, when I gave my own thesis presentation. And in case you're wondering what that says, better lean in because all my fonts are going to get a lot smaller. But I had to even look it up. The title of my thesis was Derrida and Dynamic Precipitation. Yeah, so I'm not going to talk about anything like that remotely today. I won't say I've left Derrida behind, but maybe he's sort of left me behind. So actually what I'm going to do is not give the sort of standard talk that I've been giving the last few years. Moving to science was not a super strange transition for me. I actually started out my life before SSU doing science-related things. But I'm going to try to sort of tie together some of the research I did in my master's degree and in my PhD, and but not with necessarily a specific thesis that I'm going to try to prove. More, I don't know, a talk touching on some things that I find interesting and finding some common threads. So the title, what I'm going to talk about is Decisions, Illusions, and Evidence. So I have focused a lot in my work on looking at decisions and how people make decisions and how decisions work in the brain. So that seems like a good thread to pull at. And illusions and evidence is just a reference to the fact that, well, in some of my research I look at what some people call illusions, but also just sort of this flavor of being uncertain about how things work and the possibility that we can be wrong about how things work. And evidence, what counts as information that tells us things about our decisions. I promise you there will be pictures of real brains from people I have worked with. So just in case you're getting bored, there is also math very quickly. But so in case you're sort of wondering when you're going to get another cup of coffee, just wait, there are brains coming. So one of the threads in sort of these things is just as we think about decisions, a common sort of paradigm or sort of split is to think about the nature of our decisions in terms of whether or not they're automatic or optional. This sort of this tension of their way in which a lot of decisions might feel determined or might feel free, or we might have philosophical frameworks that say our decisions are more determined or free. And I'm not going to prove anything one way or the other, but just sort of talk a little bit about how some of these questions come up in different sort of work that I've done. So in this sort of moseying along, I'm going to sort of touch a bit on scientific methods, how we explore decisions, some of the philosophical issues, and hopefully even, if time permits, talk a little bit about normal life. So here's a decision. I came to SSU in the fall of 2002. And this decision happened somewhere in the lead up to my coming here. So in January of 2002, I lived in Ottawa. I was working for an organization called Christian Horizons. I just left doing a degree in aerospace engineering. That was a while ago. And at some point in September, I arrived here. I arrived in St. Stephen. If you can't read that, it says I arrived in St. Stephen with $5. I was dropped off by the bus out at the Red Rooster. And I didn't know that the bus didn't take me to town. I didn't know many things. And I had $5, and I had a piece of blue corduroy for a towel. Now, what's interesting though, if we want to explore this decision, me coming to SSU, the first thing we got to figure out is when did it happen? If we want to start poking at this decision and understand something about its nature, we want to know, when did I decide to come? And this is not an easy question to answer. I know that I came, and I know there was a point in time before I came, and I'm not sure exactly where on this timeline I decided. And it might be that for many of our decisions, this is a difficult, if not impossible, thing to figure out. It might not be that our decisions are always so clearly located in time. But this does touch on our first sort of issue, philosophical issue, if we want to explore the nature of decisions. It's what we might call the time constraint. How do we constrain our study of decisions in time? Where is the thing, the point in time where we can point to and say, here's where the decision happened? So, oh yeah, so I do have some photographs of me during my time at SSU that I lifted off the internet from Heather Mercer. These are all Asia trip and Europe trips. So this is like 2005, 2004. I did actually come here. There is photographic evidence. So I left here and shortly thereafter went to the University of Edinburgh to study philosophy. My focus, the focus that I worked there is I worked in an area called philosophy of mind, which I won't sort of explain at all. But my dissertation focused on research involving this question. So there's this a research psychologist in the US named Daniel Wagner, and he's written this book called The Illusion of Conscious Will and some other things, exploring the idea that our experiences of will, the sense you have that I am making a decision, or that the feeling I have before I act, this thing that we might say is the conscious experience of our will, is an illusion. It's not actually doing any work in creating our behavior. his question he's going to explore is, does our feelings, our bodily perceptions tell us the truth about what we're doing? What does that information tell us about our decisions? And he wants to poke at this thing, he wants to explore why we can be wrong about why we're doing things. So the title of my University of Edinburgh dissertation, I've left it in small print because it might be the worst title ever. I will read for you out loud, and hopefully you'll stay awake. It is called Conceptual Constraints in Empirical Investigations into Consciousness and Behavior. A thrilling sentence. What can you do? So Daniel Wegner is interested in decisions, and he sort of falls in the philosophical framework of determinism, roughly. He's actually not a philosopher at all, and so he totally misunderstands a lot of the nature of the debate that he participates in. But he falls within a particular stream that's going to say all of our behavior is determined. You have causes running down from original causes that strike up into other things, and that eventually produces everything we see. There is no sort of break, there's no spot, a gap in the cause and effect chain that leaves us room for us, for our will. And he's got a couple of experiments that he's going to show us. So this is an experiment that you can't really see what's going on here, sort of a bad picture. I had a hard time digging around for better pictures. Here's this experiment where you have two people looking at a computer screen, and they've got a mouse with a little board on it, and they've both got a set of headphones on. And what's happening is they're listening to things through their headphones, and they think it's sort of random. And one of these people is the subject of the experiment, and the other person is a confederate of the experimenter. But the confederate is unknown to the experimenter, to the subject. The subject thinks they're both subjects. And what's happening is they're moving around the mouse. They both got their hands on this board, and they're moving it around. And every now and then, they stop at a particular object on the screen. And then the question is asked every time, how much did you think you were controlling where you stopped? And the subject's supposed to rate, I stopped it here, or the other person stopped it here. And so what they don't know is that sometimes they are hearing things about different objects on the screen. Let's say the word duck. And just after they hear the word duck, the confederate is going to force movement to the duck. And what you find out is people often say that they were the one that forced that movement. Mm-hmm. And this basically is the crux of this whole argument. He's like, hey, shouldn't you know when you caused your own behavior? Shouldn't you know when you've made a decision? How can you be wrong about something like a bodily action? And he's going to say, well, the way this is happening is we think that when we have these thoughts in our head, what he calls the apparent causal passive, no one has a laser pointer, do they? Or a stick? All right. I like sticks. So he says, we think that the way that this works is we've got a thought, we've got an action, what he calls the apparent causal path. And so you have this sense in your head, oh, I've got a thought about a duck, and I move that thing towards the duck. But he's going to say that's actually not how our decisions are formed at all. Everything is going on from unconscious causes to action. So there's an unconscious cause of our thought and an unconscious cause of our action. And these are the things that are doing the real causal work of causing our behavior. There is no relationship between our thoughts, no mechanistic relationship between our thoughts and our actions. And the basis of this is we can be wrong about why we did things. So this is an interesting way, I think, to explore issues of our decisions. And I'm not going to go into nearly all the stuff I explored in my master's degree, but the broad conclusion of this is that the sources of our experience that produce a sense of agency, whatever it is inside of us, our body, these sort of mechanisms that tell us we are in control of our actions, it is not infallible. But I think we can probably live with that and not think that it's entirely an illusion that we are in control of our behavior. And the second conclusion we can draw from this is that it's also just not clear how to connect our experiences of being in control with the causes of our behavior. So these are the conclusions I would draw from this research into the causes of our behavior. and our actions, as opposed to the conclusion that it's all an illusion, that our mental stuff controls our behavior. And I think these are also conclusions we can live with, that it's not clear the relationship between our mental stuff and our outward behavior stuff, and it's whatever does that work is clearly not infallible. The systems that monitor the sources of our behavior is not perfect. So the second issue in sort of, if we want to go out exploring our decisions, the first one is this constraint of time. When in time do we look to find a decision that we're going to poke with a stick? But also, what is the thing that we are probing or observing? So the whole point of my dissertation was actually to say the problem with these sorts of explorations of decisions is what I call the conceptual constraint. What goes in the box that we're calling a decision? Is moving a cursor on a screen with two hands on a mouse, is that a decision or not? How do we define what's in the box so that we can now take measurements, poke with sticks, do whatever we're going to do as we explore decisions? So this is the second sort of issue about exploring decisions, the conceptual constraint. And then just a little bit more about this. So before we move to brains and things, I just wanted to touch on a little bit of interesting behavioral psychology that relates to some of these things. Like, I think it's important that if we're thinking about decisions, we realize that we are not as free as we think we are. If we think about this tension between sort of things being automatic and things being free, we would like to think we're fairly free. But before we move to the neuroscience, because neuroscience basically just sort of forgets about that entirely, we just sort of look at automatic processes. But don't be surprised to learn that much of your behavior is produced by things that you have no awareness of, that you're more on the automatic side than you might think. So a brief illustration from behavioral psychology. So I don't know if has anyone here seen a talk by Dan Ariely or heard of his book, Predictably Irrational? Yeah, wow, the psychologist. So he gives this example. So he says, look, this is a figure showing the percentage of drivers in different countries that agree to donate organs on their death. In Canada, when you get your driver's license, or when I did, on the back of the form, or whatever, you can tick a box that says, I agree, in case of whatever accident, to donate my organs. And so he's like, look at this interesting chart. What's going on here? Why do you have such a wide spread between this group of people who see almost perfect participation and this group that sees almost the exact opposite? Especially when you see societies like Denmark and the Netherlands that are known for being sort of more progressive liberal societies. But then you also see like Sweden over here. So what is going on? And or groups of countries like the UK and France like being so completely opposite when they're so similar in everything else. So what's going on here? What is the reason for why you have this huge split in people agreeing to donate organs? And I mention this because it seems like here we've got a decision in a box. You either decide to donate your organs or you don't. So what has brought this about, and why is it different in these two different groups? Well, did anybody have any guesses? What could explain this? Cultural differences, yes?
You have to.
No, so that's not the answer. That's a good thought, right? It could be that you're forced to. Austria, you're forced to. This is all voluntary. So it is a genuine decision. Yes, in the back.
Similar to that opt-out versus opt-in.
Boom! Exactly. Right? These countries, you have to tick the box to be part of it. These countries, you have to tick the box to be out. So, who decided to donate their organs? Their context, i.e. the framing of the question, basically determines who's doing it and who's not. So, another good example from Dan Ariely. So imagine you've got two choices, A and B. And A is really great in attribute A, attribute 1, and B is really great in attribute B. So these are like two trips. In this trip, you go to Paris and it's all-inclusive food. You have to pay for your lodging. This one you go to Rome, no food, lodging is free. Something like that. Two different attributes, food, lodging. This one's really good over here. This is really good over there. And you think, okay, so if you ask someone, which would you rather have? you'd think, well, I've got these preferences internal to me, and I'm going to just weigh them out, my preference for food versus free lodging, and I'm going to make a decision. And it's going to be a clearly separable decision based on my feelings about A versus B. And Dan says, okay, now what would happen if I introduce a third option, A? It's the same as normal A, except it's a little bit worse. So let's say instead of all your food, this is just breakfast and lunch, no dinner. What is that going to do to your choices between A and B? Because one mode of thinking would be, well, nothing really has changed. I still have my preferences for attribute 1 and attribute 2. The fact that I've got a third worse option shouldn't influence anything at all. Right? I'm making a choice, free decision. So here's an example of this. You've got, I don't know what The Economist is. So The Economist, very briefly, at one point in time, offered 3 different options for subscription to their service. The first option for $59 was an online-only access, no print. The second option was a print, so it's $59, $125. And the third option for $125 is print and web. So we've got web, just print, both. These are the same price. Right? So it's our A versus B with a worse A. So, and if you ask people, what would you prefer? But with only 2 of those options, this is what you get. So if you say, okay, we've only got the $59 one and the $129 one, 68% of people say $59, I only want the web. 32% of people say, I want the web and print. Now we add our third option in, and what happens? It flips. Isn't that strange? Suddenly, by making a worse option in the middle, everyone thinks this option's way better. So how did they decide that? Who decided that? What was it that made that decision happen?
Marketing problem.
Yeah. Exactly.
Yeah, I mean, so marketing is you know, what's the word? You know, enacted psychology, right? I mean, and so is advertising and everything like that, right? You know, you don't necessarily care about the framework or the rightness or the wrongness of it. Does it work? And clearly, it does, right? Third worst option, and so this is interesting in that if we are thinking about our decisions and we want to go poke them, we have to think about this thing. You know, I'm going to call it the location constraint. Where do we look to understand the mechanisms of our decision? So we've got a time constraint. I need to know when a decision is happening. I need to know what goes in the box, and I need to know where this box is. What is the limits of this? Is the box just inside my head? Is it my body? Is it my body in a particular environment? What are all the things that are causing my decision to happen? So, thus ends the sort of philosophical portion of the talk. These are sort of the issues I talked about in my master's degree, and in what feels to me like a very small move, I then went from here and decided to explore how decisions work in the brain. Because for many people, oh, actually, yeah, right. So this is the thing of where and when do we focus our investigations. You know, if they're more automatic than we would like, and we're influenced by factors that we're unaware of, where do we focus our investigations? And the natural place to go is the brain. But I don't know if you can see here, but I use one of my favorite words in the small print here. This is sort of a thought that is currently in vogue. The brain can tell us everything about how and why we do things. I don't believe that. But this is sort of the focus of a lot of certainly pop psychological research and certainly pop psychological marketing. The idea that if we sort of slap a brain label on things or use this nifty neuro prefix, ta-da, we know more about the causes of our behavior. And if we want to know things about decisions, we should really just go start poking around in the brain. Anyways, but I don't actually think that's true. So the first kind of question we want to ask ourselves, if we are going to think that the brain tells us something about our decisions, is what sort of information does the brain tell us? What kind of information do we get out of the brain, and what can this tell us about our decisions? I'm going to show you a little bit about what we've been learning from the brain. This is, again, I don't think you can see it here. Under that very exciting subtitle, Models, Math, and Computations, there's a little bit of text that says the most exciting part of my talk. I'm gonna talk a little bit about. Oh, there you can see it. That's better. Computations, the most exciting part of my talk. This is my much more exciting thesis title for my PhD from last year. You can read it silently inside while I read it aloud. Reinforcement learning describes the computational and neural processes underlying flexible learning of values and attentional selection. Maybe, I don't know which is the worst title. I say this is the second worst one. You can discuss amongst yourselves which is the worst title. But yeah, maybe it's been all downhill since Derrida. So all this talk about computations, I'm going to give a little bit of a brief overview of cognitive neuroscience, some of the methodology that I've used. I'm not going to give a lot of data in my talk. I'll show you a little bit about how neuroscience research works, the kind of stuff that I have done, and a little bit about some of the things that I've learned. Computations are up on the screen because the sort of neuroscience that I do, neuroscience is a really big category of kinds of research, which includes everything from looking at cellular processes, how voltage-gated channels change in the presence of sodium and calcium, all that thrilling stuff. I don't do anything like that. And if it's also like putting people in giant magnets, fMRI, I don't do things like that. I do something called computational and systems neuroscience, which means I look at how systems in the brain work, so how information moves across different areas, and I do this via building computational models. So the idea being that certain processes in the brain, like making decisions or learning things, involve computations, acquiring information, updating that information, comparing information, and all of this, these processes can be related to computations. So I will show you a little bit about all this very exciting stuff. So what's happening in the brain when we learn and when we make decisions? So this is a little bit about some neuroscience methodology. So this is just a schema to let you have a framework for everything that's going to come after. So traditional neuroscience works in either one of two ways. Either you have behavior, something like pushing buttons that you relate to observations in the brain. So you can use different methodologies to look inside the brain, let's say like EEG, something on the skull, or fMRI, someone in a scanner, or other sorts of things that I'll show you involving electrodes that I get to do. But you relate in a one-to-one, contrast in behavior. What's the brain doing when I push the button? What's the brain doing when I'm not pushing the button? And looking for relationships in that way. And you also do the other thing. You relate what's going on in the brain to what we call cognitive processes, which are things like learning and memory. These are descriptions of sort of bigger functions that are probably distributed in the brain, not located in one area. But again, we relate sort of things like learning a cognitive process to observations in brain data. And what I do is I do this thing here. So I build a formal model that explains both the behavior and the cognitive processes and is meant to provide an insight into brain data. Learning is not a uniform, singular thing, like you have a giant chunk of your brain that sort of turns on and off as information comes in, but a very fine-grained process that involves lots and lots and lots of interactions at a very fine scale. So the best way we think to try to make sense of this very fine scale is to build a formal model, and I'll show you what that is in a minute, to understand this behavior. So this sort of sits in the middle, saying, okay, I can use my model to predict behavior, to describe these processes, and relate to brain data. So this is not a formal model. This is like a conceptual model. And it's a conceptual model that informs a lot of my work. So the computational framework that I use is something called reinforcement learning, which I won't really talk that much about. Reinforcement learning is just a framework that says, this is how we learn the world. We have a world that gives us information in our sensors, and we choose actions based on our previous experience with these sensory information. and then when we make a choice, something happens, we get new information about our environment, and then we update our predictions about what's going to happen next. And that's how we make choices about actions. We compare previous experiences in particular environments with what we think is going to happen. So this is the conceptual framework that I live in. This is, I'm only showing this because this is a figure from my first publication, that is my conceptual model of how something called attentional selection works. And there it goes. And this is, so this is the experiment that I designed, trying to get at, solve some of these problems of constraints, time constraints, and location constraints, and conceptual constraints. So I'm not going to focus too much here, but the thing you need to see in that very small A panel there is how the experiment works. So in this experiment, you sit in front of a touchscreen computer, and there's going to be a little cross. So the top panels are the screens that you would see as a subject, and the bottom is sort of a timeline, so how long each thing happens in sequence. So you get a screen, across the little screen, you're supposed to look, not move. Sort of gives me resting, a contrast of what you're doing, what's happening in the room, and doing nothing. Then two things are going to pop up on the screen, a circle and a triangle. Thrilling, I know, but the nice thing about circles and triangles is you don't have a lot of affective response. You don't have very strong feelings about circles and triangles. And then at some point in time, this cross is going to be removed, and that's your go cue. Now you get to do something. You're going to take your finger and you're going to pick one of these things, and then you're going to hold your finger down on the space bar, and you're going to get something, a gold star or not. And your job, all I tell you, is get as many gold stars as you can. And you don't know anything about the guts of it, right? So you don't know that the colors are going to change. So the secret is that there's a relationship that changes between shapes and colors and stars. And you need to learn this, but I'm not even going to tell you that that's what you have to learn. You just have to learn the reinforcement that's going on. So don't worry about the rest of this slide. This is a figure from my second publication that just came out in Frontiers and Rose Halls. I don't know what the problem is, but I just have the worst titles. But in my defense, getting things published is usually a matter of committee, i.e. you give things off to reviewers and they tell you how dumb you are and how terrible your titles are, and they fight you over words. You end up producing a hybrid. You know, my first title was amazing. This is what ended up coming after the fact. So this is roughly the schema for how I think this is working in the brain. So this is meant to describe sort of the cognitive functions of how someone is making these choices. So if this is the sequence of what's happening in your behavior, you get this option between a circle and a triangle, and you pick the circle and you get a gold star, and then you get a triangle and square, you get a gold star. This is sort of what's happening, and you have had all these experiences, and you need to figure out what's predicting the gold star. And I say, here's one idea of how this might be working in the brain. That you have something in your brain called a value function that gives you values for stimuli in your environment. It says colors and shapes and tables and floors. Everything has some sort of value to you based on your current biological needs. And these values are compared to each other. And then you're going to use a selection function. You're going to compare all the values of everything that's available to you, and you're going to select the thing that is most likely to give you a positive outcome. There's tons more going on in there, but I'm not going to talk about it at all right now. This is what a formal model looks like. Calm down. So the advantage of a formal model is this. Very specific predictions. So by formalizing using math, exactly what I think the values for any stimuli are in your environment, I now have constrained my investigation of decisions in a very specific way. And I will say, at this point in time, you know, and because I'm tracking all of what people are doing in time, and later on simultaneously with some things in their brain, and I say, at this point in time, they're looking at this screen, and I think that the value that they have for a red thing versus a green thing is this versus that. And I'm going to predict that on the very next thing, they're going to make this choice, and I'm going to see something happen in the brain in this way. That is going to be different than if you had two other different choices. So this is, so by using a formal model versus a conceptual model, the rough picture of how things are working, I can now have very specific predictions. So this is just a reminder of where this is situated. So I've got some behavior. My formal model is meant to both predict their choices. I'm going to use this information, these specific things to say, okay, this is what their behavior is going to do. But it's also predicting what's going on in the brain, and hopefully it's describing roughly how our mental machinery is working when we're making these choices. The brain, for real this time, with pictures. That's what that says. So what kind of evidence information can we get from the brain? So this is just sort of a very brief primer on the different modalities and methodologies we use for investigating the brain. So has anyone seen images like this before? So what are we looking at here? What are these images of? Anybody know? Brain. Does anybody know the word for the kind of images these are? Walter knows. So these are MRI images, which stands for magnetic resonance imaging. And these are actually functional magnetic resonance imaging images, which means that you have, so all this gray-white stuff is a picture, a cross-sectional picture that's been taken of someone's brain that is showing their anatomy, roughly. It's said to fully understand fMRI, you have to understand quantum mechanics. So this involves a lot of very complicated physics to get this sort of image. It's certainly not like a picture. Even though we think of this as a picture, this is an image that's produced via a lot of math and a lot of assumptions about different things. And that's true for the anatomical image you see in all of these things. But more importantly, you see those colored blobs. These are the things you see in newspapers and on TV. They say, hey, if you think about tennis or if you feel angry, look at these colored blobs that happen in the brain when you're thinking about those things. You do not have colored blobs in your brain. So the upsides of using fMRI, so this is where you lie on your back and they put you in a giant magnet. So has anybody other than Walter had an MRI? Yeah, a bunch of people. Me too. Okay, side note about MRIs. When you're a junior scientist, you're always looking for early volunteers for your experiments. And so as a research community, you tend to share around, you're like, oh, if you volunteer and do this thing for me, I'll do it for you. And of course, early volunteers for me involve people like touching a screen and getting little stars. I volunteered for a girl who uses something called TMS, which is transcranial magnetic stimulation. So we're using a very powerful magnet to intentionally disrupt activity in your cortex, with the intention of sort of looking at what happens when you're doing it, without this, and then what happens when you're doing this. Wow, bam! This magnet discharges at a very specific area. And the whole idea of that is this sort of the nicest kind of proof we have that anything is involved in producing a behavior is the elimination proof. If you don't have that, or if it doesn't work, it seems like it's necessarily involved in producing behavior. So I volunteered for that. And she also, and as part of that, I had to get an MRI, and so I have cool MRI pictures. These are not my brain, but
Was she the one who made people into temporary psychopaths?
No. This is no. This was a visual area. Oh. So MRI is a great tool to learn things about the brain because you don't have to cut open people's heads, but you get to kind of look inside them. But there are some problems. So you don't actually see brain activity. So fMRI, the signal that you get for looking at the brain, how they produce these images, is something called the BOLD response, blood oxygenation level hemodynamic response, which just is saying that the magnetic properties of blood in your brain changes as it's used by synaptic processes. So we think it's a surrogate signal. It's not direct brain activity, it's this other thing. But also fMRI has poor spatial and temporal resolution. You can only look at chunks of your brain like a millimeter cubed, which has thousands of neurons. And we can only look at slices in time of something like a few seconds. So the time constraint is a real problem here. If we're thinking that you've got an option between A versus B, how much time does it take to make sure to make that decision? Is it on the order of seconds, or is it on the order of milliseconds? So there are some advantages, but there are also some issues to using fMRI as investigative modality. I'm not going to show you this No, we're going to skip this. So one of the other ways that we can investigate what's happening in the brain, I was very tempted to give everyone a brief little bit of overview of neuroanatomy, but I'm not. So another way that we can look at what's going on in the brain is to look at electrical signals that your brain is producing directly. So information in your brain is communicated via cells that synapse with each other. They connect to each other, and they share information via the opening and closing of little gates on the cell bodies that produce what's called an action potential. So I'm not going to talk about those mechanics at all, but basically information is communicated via electricity in your brain. And when you have a lot of electricity in a particular area, this generates a fairly large current. And for all of you who remember your basic physics, electrical currents produce simultaneous magnetic fields. Yes? Yeah, somebody over there, magnetic fields. Anyways, so we can use measurements of magnetic fields and electrical currents in the brain to also tell us something about what cells are doing, who's talking to who, where things are going on, when different things are happening. So has anybody ever had an EEG cap? You know, like one of these things on the surface of their skull, you know, or these little suckers that you see sometimes. So EEG stands for electrocorticogram, and it's measuring the magnetic field that's produced by this electrical activity in the brain. But you can measure these electrical fields and these magnetic fields internally as well. So you can put electrodes directly below the skull and via a few different kinds. So you can have depth electrodes, so these are ones that go way down in, and you can have surface electrodes, ones that stay on the surface of the cortex, and they can be strips and they can be grids and all sorts of stuff. And I mention all this because this is the modality that I use. So I worked at Toronto Western Hospital with a surgeon named Taufik Daliente, and he implants electrodes that look like this directly onto the surface of brains like that, because he is a surgeon that helps people with advanced degenerative epilepsy. So the end of the path for someone who has degenerative epilepsy is not a pretty one. So if drugs aren't controlling your seizures anymore, these seizures are going to contribute to different sorts of declines, motor declines, cognitive declines. And the last sort of final option, therapeutic intervention, is a surgery called resectioning, where the surgeon's going to go in, he's going to remove the place where he believes the seizures are originating. And hopefully not a lot of other bad things happen to you. It sounds terrible. It actually sounds sort of like futuristic Stone Age stuff, but I will say this. So the patients that I work with, it is sort of like, you know, it is that sort of thing. And we have all this amazing technology, so we can go in and, when you talk to these people who are candidates for the surgery, the impact of their epilepsy on their lives is so incredible, is so powerful, that they are willing to risk a lot to eliminate the possibility of seizures. So let's say the surgeon decides he needs to remove, and by remove, I don't mean like cut out, like, you know, minuscule portions. He might remove a significant chunk of a lobe. And so, because the worst would be to not get it all and have your seizures come back. So let's say he has to remove a big chunk of my motor strip on this side of my brain. This is going to cause contralateral paralysis, maybe up to half of my other side of my body. And these people say, yes, I would give up my arm control to not have seizures anymore. These are people that can't live on the road, can't drive, can't do anything. So in order to find the surgical site that he's going to remove, he implants these electrodes and then monitors what's happening. So he first thinks, I've got a pretty good idea of where these seizures are beginning via external monitoring methods, but the best thing he can do is put electrodes as close to the possible site as he can. And this is what that looks like. This is a CT image of someone who's had a grid implanted. This is sort of the schematic of where these grids are implanted. So this is on the left hemisphere here, sort of a frontal area, and then these strips are placed into your hemispheric space. This is one of my patients that I work with. And this is a real brain of someone, another patient that I work with. So they've had a partial craniotomy here, and they are having a grid and strip implantation. So this is a picture taken by the surgeon to help him locate after the fact where his grid in fact is. And this is another patient again, so you can see the CT image on top for where that grid is implanted, and then that's a picture of what this actually looks like. Yes?
Is this something that, like, you remove it, put the things on, do your thing, and then take them off and do it up, or you?
These are semi-chronic, so they stay in for a month. They're just there to observe what's going on, trying to find the epigenetic origin, which is going to be surgically removed. I also collaborated a little bit with another surgeon, Andres Lozano, who implants chronic shaft electrodes. So this is the world-leading research at Toronto Western that is using electrodes, chronic electrodes, to regulate activity in the same way that we have pacemakers. So it's a pacemaker device linked by a wire, and this was originally developed to control Parkinsonian dyskinesia, so movement disorders. So before this, and what still happens sometimes, is if you want to stop people from moving erratically when they have Parkinson's, you go in and lesion their thalamus, basically destroy it with a little stick. We're trying now to use an electrode that discharges a small electrical signal, and we've discovered that we can use this technology to help us with other things, like even depression. I work with a patient with major depressive disorder who had a shaft electrode that stays in there, and there's a subcutaneous wire that lodges to a pacemaker thing. This is not that. This allows me to see directly on the surface of the brain the electrical signals that are being generated by the tissue underneath. So, back to what my experimental paradigm and what's going on in the brain. How do we make a decision when we have two possible choices, square versus triangle, and what is the brain doing when we select between these two choices? So this is now a reconstructed image showing in 3D space the location of a set of electrodes for one of my patients that I'm going to use to investigate. So my location constraint is a very specific part of what's called ventromedial prefrontal cortex. So front, middle, sort of right behind your eyes. And this is the location constraint, the time constraint. I'm going to look at this very specific slice in time. And I'm going to assume, because I'm a good scientist, that none of the environmental factors, there's no third worst option. You really are choosing between these two things. And so I collect electrical signals, let's get that, and use my models to make predictions about, at every single point in time, what is the value of A versus the value of B. And that is not a very big slide, but what this figure actually shows is that in very certain electrodes, there is a signature of activity that is directly related to the value between your two options. So I have this crazy mathematical model, and I can predict on every point in time exactly how much my model says you value these two things. And I can predict, so this is from a single subject that I work with, and I can predict this person's choices better than 80% of the time, just using math, what they're going to do. And then I use the values given by my model, and I say, hey, look, these values predict power changes in 4 to 6 hertz with specific electrodes. I'm not going to explain any of that. So there's a relationship between this electrical signal and the values given by my model. So this is the side note, right? So I sort of started off by saying we're going to talk about automatic versus optional things, and that sort of has all gone by the wayside. When it comes to investigations of the brain, there is no sort of like even inclusion. I mean, first of all, if you talk about free will in neuroscience, you wouldn't work in neuroscience unless you had significant, awesome tenure and could do whatever you wanted. But even then, you probably wouldn't. So free will and optionality is sort of placed on a shelf over here. The investigations into behavior is assumed that the stuff that I can poke in the brain is at least the proximal cause, the direct thing that is producing your actions. I would say that in my models I do account for the fact there is a stochasticity element, that the idea that it's not clear how these values are interacting, and I put that in a box called stochasticity, called beta, and it lives in my model too. I think I've run out of time. I was going to talk about normal life a little bit and the work I do now. Yeah, this is not sort of normal life. So I just showed this very briefly. I'm now working as a scientist for this company that is trying to build a system that helps people make difficult decisions in complex medical situations. So I'd love to talk to you about that, but I won't talk about that right now. So that's all. So I I think we have a few minutes for questions. Yeah, if you want to ask me any questions, I'd be happy to diagnose you. Yes.
Who currently is most interested in the kind of work that you're doing? Like you're working for this company that's trying to help people making difficult decisions.
Yeah.
Marketing is obviously somebody who's very interested in the kind of work that you're doing. In general, then there's the academic community wants to know how we learn, why we do what we do.
Yeah.
Who's most interested in what you're doing?
I mean, so as cool and awesome as I make my research look, the truth is that it exists in a very, very small little side path of things, in which my publications will be read not even by my parents, there's that kind of niche and obscurely technical. In a bigger picture, the world in which this work happens, who cares about that? Well, the thing I thought about doing next, so rather than going and working at this tech company, what I wanted to do was try to connect my work and understanding how decisions happen in prefrontal cortex with problems when neuropathologies related to decision making. So we know things about schizophrenia being related to problems, dysfunctions, neuropathologies in the same area of the brain that I research. But we don't know the link between some of the behavioral deficits you see in pathologies like schizophrenia and the mechanisms that I'm looking at. So this is one of the research overlaps, is people who are trying to make these connections between high-level behaviors, maybe some genetic causes, and trying to understand the low-level mechanisms that are impaired. Especially if, let's say, you wanted a very specific targeted therapy, like a drug or an intervention that only got at the thing that is broken in that area. That would be one application of this kind of work. In terms of marketing and stuff like that, I don't have anything that is breaking ground on learning or decision making. I'm not an experimental psychologist or anything like that, so I'm not really breaking ground like, hey, it turns out all this stuff. No, in working in cognitive neuroscience, it's trying to understand the most boring decision you've ever made in your life. I would always tell new subjects, hey, do you want to do my experiment? It's like the worst video game ever. What is the brain doing? And because the truth is, we don't know. I love telling people, neuroscience is the Wild West. We cut massive hunks out and nothing happens. Or you get a concussion and you can't remember your mom. There's a lot that we don't understand. So yeah, it's kind of exciting in that way. Any other questions?
With the philosophy of mind stuff more, I guess it's sort of I'm interested in this or whatever, but with decision making kind of having all these kind of external influences on the way we make decisions, I guess I'm wondering if you could suggest some way to kind of, get past that or something
So philosophy of mind is a funny thing in that, what I realized through my time in that is that I'd rather be doing cognitive science. Right? So philosophy of mind is really, talking about these investigations and not really doing them. So, asking all these questions about methodology, like when you use the word decision, what do you mean? When you use the word mind,
right,
what do you mean? And so, and there's a lot of good work and useful things happening in there. So I don't necessarily know how to link directly sort of philosophy of mind things to these issues about that are sort of more well known in the domain of behavioral psychology, like what's known as framing. The fact that I can put things into your environment that are going to cause your decision to go one way or the other. If you've ever had a chance to read Thinking Fast and Slow by Daniel Kahneman, he's this Nobel Prize-winning guy. So he lays out sort of a lot of these sorts of well-known behavioral psychological phenomena that just seem to be part of the way that we work. And I can talk a lot about that, but yeah, philosophy of mind is sort of a different sort of ballgame. Here's where I left it. Yes?
So, I'm not sure if people have often heard of a guy who got a piece of rebar through his head.
Yeah, Phineas Gage, yeah.
Yeah, right. So would your model be adaptable to then still be able to predict? He's a different individual. Would it change, or?
He's a different individual.
Well, people would argue that his personality is completely different. He no longer treated his wife the same. He would arguably make different decisions. So would it change the model or not?
I mean, strictly speaking, no, right? I mean, so this model isn't making predictions about, and the model I use is like, variations on like 1,000 other more well-established models. That's not sort of the novelty of what I've done. But the model isn't making predictions about sort of things at the level of personality. It says, essentially, you've got a signal that originates in the brainstem called a reward prediction error, which is the difference between what you thought was going to happen and what is going to happen. And these dopaminergic neurons project to prefrontal areas, and then these areas have to keep track of the value of things in your environment, like how good is this banana versus how good is that muffin. And the model is going to say, is just making predictions at that level, at what these sort of groups of cells are doing in terms of processing this information. And if it didn't work because he's lost a big chunk of this part of his brain, well then, that doesn't really bear on the model. It just says, hey, look, the part that is necessary for this to work is gone now. We could probably talk a lot about persistence of identity through time in relation to body versus behavior, but we won't. Yes.
But of course,
Probably last questions.
I understood everything that you talked about.
Great!
But I'm going to go back to something really simple,
Okay.
the economist example.
Yeah.
Because we look at that and we think, well, what idiot would make those choices? Well, Dale and I did. Which I think, but I think in terms of the how you what you factor in. So if I were making a decision, I would have consistently gone with the online subscription. If he were making the decision, he would consistently have gone with print only. But if I was paying for it, I would have still stuck with web. But if he was paying for it, it wasn't costing him anything to allow me to also have access.
Yeah.
And then we can also consider that we bring the print subscription into SSU, so that that factors in. But anyway, so my point is there a difference if we're making a decision only for ourselves, or if we're considering other?
Oh, sure, right. So I mean, I only raised that example just to say that like where a decision is located in time and in space. So all this stuff you're talking about makes it seem like when you come to have to like push a button on a computer to pick an option, maybe your decision isn't happening then. Maybe it was happening at a previous point in time. The only thing I would say about sort of like being very confident in what you think you would choose is the whole point of examples like that is it's kind of surprising when you actually do experiments, seeing what people choose when they're put in these sort of funny circumstances, that it seems like when we go to make some of these decisions in the moment, some of these other things that we wouldn't think have an effect do affect us. And because we like to think, yes, I've done the math, I've added it all up, and that's what's producing my behavior. And this is just this idea that it's maybe hard to take into account all the things. Context matters more than we think, which is scary.
Okay, thanks. I just wanted to make one quick comment in regard to Stefan's question because it shows the value of interdisciplinary thinking. Recently, the whole Phineas Gage story has been somewhat retold because historians of science, which are very important contributors to the whole science enterprise, have told us that they've looked at this whole thing more closely and realized that all those stories about how much he changed have been blown up for the sake of how good of a story it made. And there's all kind of evidence that the changes in his behavior were not anywhere near as significant as you were told by me. So we need historians of science in order to do science well. That's one lesson we learned. And also knowing what Matt was saying about how we don't actually have any free will decisions. I knew Matt would take the full hour, and so I asked Kara to promise that she would actually leave us a break time. So you'll have a slightly longer break, I think, after Kara's talk. And this time we'll just do a quick stretch break. So can you take a quick stretch break? If you absolutely have to leave the room, please come back in just 2 minutes.